Hello, you beautiful people. So this lecture is about the solution for the ammonia reactor. In the last lecture I showed you the new layout. This was basically that we have a reactor with the injection of fresh feed to the ammonia reactor to cool down the mole flows between the different plug flow reactors, and we have a heat exchanger to preheat the fresh feed to the first stage of the reactor. I gave you for the reactor I gave you some molar fractions. So you have the main inlet with 100 degrees Celsius, then you have the preheating and the heat exchanger up to 400 degrees Celsius. And then you have two injections of fresh and cold feed, 15 degrees Celsius, so they have the same composition. Here the mole flows are given, and at the outlet you know that you have 300 degrees Celsius and mole flow of 17,000 kilomoles per hour and this composition, so your reactor operates with roughly 17% of ammonia at the outlet. Okay. And your task was to answer these questions here, and yes, and yeah, you should. What was the task? The task was to get close, or to get values close to our stream 3 here, to have the same mole flow and the same composition. Okay, let's start with the basic layout. What you can see here is that I start with my fresh feed, then we have a heat exchanger. I specified the heat exchanger to an outlet temperature of 400 degrees Celsius, you can see here. And then it's sent to the first plug flow reactor. The outlet of the first plug flow reactor is mixed with fresh cold feed, so this is feed in 15 degrees Celsius cold. Then it's sent to the second plug flow reactor, and the rest of the feed is mixed here and then sent to the last plug flow reactor. For my case, I found out that a split ratio of 50% was quite good. So half of the fresh feed going to this mixer and the rest going to this mixer. And then you have the outlet here. You need to insert a recycle block, and then you can send it to the heat exchanger, and then you have your outlet here. And what I did, I focused on the composition and not so much on the temperatures and the flow. I found the compositions more important. As you can see here, I copied the slide from the PDF. I copied to DWSIM. If you think, oh, this is interesting, because then I can look at the values and compare it with the DWSIM results. Then you can do it by clicking on insert, and then you can say here, and then you can choose image. So you just have to make a screenshot from the PDF file or whatsoever, save it to your computer, and then afterwards you can insert it as an image, and then you can compare the values given here and your results. You can compare quite easily, and then you can play around with it. Okay, this is for the basic layout. Now let's go to the details. So for my case, to get a good agreement on the composition, I had an outlet temperature of 492.5 degrees Celsius, and this you can see here. And if you then have a look at the outlet temperature from the heat exchanger, then you will see it's 304 degrees Celsius. So it's not a 100% fit with the 300 degrees Celsius given in my PDF slides, but we are quite close to it. So 4 degrees Celsius, it's not such a big thing. For the heat transfer coefficient, I chose a value of 280 watts per square meter Kelvin, and with this I end up with a heat exchange area of 1000 square meters. Some of you looked up some typical values in the VDE Wärme Atlas, which was quite a good idea, and there it is said that your heat transfer coefficient should be something in the range of, let's say, 200 up to 500 or whatsoever. And with this you are in a good range, I would say. If you would have set here heat transfer coefficient of 50, then I would say it's too low. If you write here something like 5,000, then I would say it's way off. But something in between 200 and 500 seems reasonable for me. Okay. So for the reactor volumes, I said, okay, let's start with 7.5 cubic meters. Next is 8.5 cubic meters. The last one is 10 cubic meters. So in total, we have 26 cubic meters. And yeah, why should you start with a small volume? If you remember the graph that I showed you, then when you enter the first plug flow reactor, you have almost no ammonia. So this means you are quite close from the chemical equilibrium. This means with a high temperature you can have a high reaction rate, and this means that you don't need such a big volume. And you can achieve quite good conversion with a small reactor volume. So for the last plug flow reactor, you are closer to the equilibrium. This means you need a higher reaction volume. Here you can see these are the concentration profiles and temperature profiles for the first and the second plug flow reactor. So here's the first, there's the second. And what I try to do is that I have all the time, I have a temperature increase. So you start here with 400 degrees Celsius and then go up to 520 degrees Celsius. You can see that it's constantly increasing. And for the second, it's also, if you would have a bigger reactor volume here, then the slope of your curve would flatten. So here you can gas it. So it would flatten, and this would mean that you are getting closer to equilibrium. And since we want to have a small reactor volume, then I would say it's always good to be in the area with the high slopes. Some of you assumed or tried to get very close to equilibrium. I hope I remember it right. I said it's not necessary to achieve equilibrium. I think if you get close to equilibrium in all three reactors, then you would end up with a different composition at the outlet of your reactor. And since I gave you the composition, you had your objectives already at hand. Yeah, I already said for the split ratio I chose 50% for the injection, so with this I got reasonable results. And here you can see my comparison of the simulation results and the composition. So this is what I gave you, and here we have like nitrogen left over 16.66. Here I have 16.63. So this is nearly a perfect match. For hydrogen, 50.65, 50.59, so it's also very close. And your ammonia content, which is what you're interested in, this is 16.92 compared to 16.87, so also quite close. I already said I gave it up in comparison to the temperatures and the mole flow. So my temperature here is 304 or 305 compared to 300 degrees Celsius. So 40 degrees Celsius difference, not such a big thing. The same applies to the mole flow at the outlet. It was given 17,144 and I ended up with 17,530 kilomoles per hour. Okay, this is how my solution looked like. I will upload my file to the email room so that you can have a look at my simulation. And yeah, basically that's it. Thanks for watching.